Welcome to our study simulation focusing on heat exchangers in power stations, a critical component in the generation of electrical power. In this video, we'll delve into the intricacies of computational fluid dynamics simulation applied to a steam generator heat exchanger. Power stations face challenges in optimizing the efficiency of heat exchangers, balancing the need for high thermal transfer rates with the potential issues of fouling and particle deposition. The deposition of ash particles, for example, can impact heat transfer surfaces, affecting the overall performance of the system. Our primary objective is to employ CFD simulations to understand both the macroscopic fluid dynamics using Eulerian methods and the microscopic behavior of particles utilizing Lagrangian methods within the steam generator heat exchanger. So we aim to analyze the impact of particles' interactions on heat transfer, surfaces, and overall system.
My name is Karthik Varman, unlike Suriamurthy, matrix number 205806. And for my part, I'll be explaining regarding the methodology for the Eulerian and Lagrangian method. Okay. So for the Eulerian method, when utilizing the Eulerian technique to simulate a steam generator heat exchanger in a power plant, the physical domain is broken down into grid cells, and the distribution of features like temperature, pressure, and velocity inside each grid cell is solved. Following are the steps to conduct this method. So first is define the geometry, then break down the domain. Next is establish the governing equation. Next is apply the boundary condition, and then we can select a numerical solver, and then we can implement the simulation code, and then we can incorporate heat transfer models, and finally we can run the simulation. So for the Lagrangian method, so Lagrangian technique simulation for a steam generator heat exchanger is done to track individual particles or elements within the system to analyze their motion, deformation, and interaction. So most of the other processes are similar except for a few. So first we define particle representation. Next we specify initial condition, and following that we formulate governing equations. Then we can incorporate heat transfer models, and moving forward we can apply boundary conditions. Furthermore, we can do particle interaction models, and then we can choose a numerical solver, and then we can implement the simulation code. Finally, we can run the simulation.
Next, I'm going to explain the results by using Eulerian and Lagrangian methods. Eulerian simulations analyze pressure drops in heat exchanger, aiding optimization of geometry and layout to minimize energy losses. As for discussion, Eulerian simulations are suitable for understanding the part behavior of the fluid but may not provide detailed information about individual particles or their trajectories. Next, the result for Lagrangian method is understanding how individual particles exchange heat helps in optimizing the distribution of steam within the heat exchanger, leading to more efficient heat transfer. As for discussion, Lagrangian simulations excel at capturing microscopic details, but may not provide a comprehensive view of the overall flow patterns or pressure drops within the heat exchanger. In summary, the choice between Eulerian and Lagrangian methods depends on analysis goals. Combining both provides a comprehensive understanding of fluid dynamics in a steam generator for a heat exchanger, aiding design decision and optimizations. Thank you.